we will introduce the BERT model. Large language models are based on the transformer architecture. Some early work that resulted in the modern large language models are GPT and BERT. And we will start with BERT, which is based on the transformer encoder. This figure shows the BERT architecture. We start with a sequence of tokens presented in parallel to the model. This is followed by multi-headed self-attention, which lets each position attend to the all positions. This followed by normalization and feed-forward layer and some skip connection. And then finally, another set of normalization. This is just one encoder. The full encoder is built by stacking multiple of these blocks on top of each other. This is not shown in the figure. Another thing is that not shown in the figure is the positional encoding on the input. So BERT is an abbreviation for bidirectional encoder representations for transformers. The transformer was an encoder-decoder architecture coupled with attention. BERT is simply an encoder, and we pre-train it with two objectives known as masked language model and next sentence prediction. Once we have pre-trained it with these two objectives, we will fine-tune the model for the end application. And this can be done to use BERT for one out of many language tasks. Previously, transfer learning in natural language processing was typically only applied to the embedding layers. We saw how we could train embeddings and then use them in separate model. With BERT, we will train an entire model and then fine-tune the full model for the end task. Let's have a look at the inputs and outputs for BERT. The input consists of the first sentence, sentence A, and the second sentence, sentence B. Each position has a corresponding position on output, and each output is a softmax over the entire vocabulary. So we have multiple softmax layers next to each other in the figure. These two sentences are separated by SEP token. Similarly, the second sentence is ending with the same type of token. The first position has special classification token, CLS, on its input and produces a classification output, TC. Let's look at how we can use the inputs and outputs for pre-training of BERT. So the first of two pre-training objectives is known as masked language modeling. For this objective, the goal is to predict a missing word similar to how we did in Word2Vec. We do this by randomly replacing 20% of the input tokens by a special mask token, and then the goal is for the model to recreate the original sentence. Let's have an example. We have the sentence, "My kid is a smart one." We will mask one of the tokens and make it as "My kid is a," and this is mask 1. This is a special token in BERT. And now the goal for the model is to recreate the original sentence. The second pre-training objective is known as next sentence prediction. In this case, the model is supposed to determine if two sentences logically follow each other or not. We will present two sentences separated by the separation token, and the model should predict true if these two sentences logically can follow each other, or output false if they don't logically follow each other. Let's look at an example. The man went to the store and he bought a gallon of milk. Here we would want to train the model to output true because these two sentences logically follow each other. Let's now put it all together to see how we can use the both objective. We will train the model on both pre-training objectives simultaneously. We have a sentence: the man went to a mask word store. He bought a gallon of milk. The goal here for the model would be to train it to output the for this mask word and true, since these two sentences logically follow each other. Let's look at more example. The man went to mask store. Penguins mask fight less birds. Here we want the model to predict the for this mask word and are for the second mask word, and to predict false since these two sentences don't logically follow each other. Furthermore, BERT uses word pieces, as we can see here. Fight is split up into two pieces, fight and ##less. So this was an example of the pre-training objective. The goal of this is for the model to learn general language structure. Once it has done that, we can fine-tune the model for the end task. Example of some classic natural language processing problems and how we can solve them using BERT. The first one is sentiment analysis of text. Here the goal is we provide a piece of text as input to the model, and the model is supposed to classify it as positive or negative. In this case, we don't actually have two separate sentences. It might be multiple sentences, but we treat it as just one sentence input to the model, and the output tokens, we don't care about anything else than the classification token, CLS, which is a binary classification. We train the classification output to output true or false, where true, positive, and false is negative. Another example is spam detection. This is very similar to sentiment analysis. We provide an email as input, and the model should classify it as spam or not spam. Now let's talk about the embeddings in BERT. There are some different embeddings in BERT. On the input, we will use something known as segment embeddings and position embeddings. We start with the word embeddings. We have done word embeddings for each piece of the word. Then we have the segment embedding. This segment embedding will indicate if this token is part of the first or the second sentence. These segment embeddings are learned together with training the model. Finally, we have the position embeddings. For BERT, we learn these embeddings instead of computing them using a formula as we did in the original transformer. So in the end, we add the word embedding to the segment embedding into the position embedding. And this is what is then input to the BERT model itself.